Okay, so before the break, what we did, we looked at the response of a simple RC. Now, what we are going to do this time is a little bit different. So now what we're going to do is going to look at a slightly different circuit, which is this. Now, where the input is some Vs of t, and we are interested in determining some V of t at the output. Now, why is this different from that? Let's say, what if I made this a step function? Would that be exactly the same as that? If I look at a step response of this thing, let's say, if I say V of s, Vs of t is simply Vs times u of t. If I do that, is this the same as that circuit where we had the switch here, and we had a fixed voltage here, and the switch turned on at t equals 0? Yes or no? So is this identical to that? So how many people are saying yes? How many people are saying no? Why not? Say again, speak up. There's no starting V naught. If you think about it. Good point, very good. Because, what's happening? If I had this voltage source, why wouldn't there be any starting V naught? Say again? There's no forward current, but there wouldn't be there can't even be a starting V naught if this was my circuit. Because what is the value of this voltage source at negative t's? 0. Which means what? A voltage source with a value of 0 is what? A short circuit. So I have a short circuit, so this would have discharged the capacitor. So these two are not exactly the same. But let's look at them. Let's look at this one and see what is this response of this one. So how do we determine the response of this thing? This thing we already know, right? So we have an initial value and a final value. So if I'm looking at V of t, now with that expression that we've developed, we can find the response of this thing. So what is the initial value of V of t at t equals 0? V of 0 plus. Is there going to be an instantaneous change in this voltage? When there's a step, there's no impulse here right now, right? So there's no infinite current. And there's a resistor here. So the voltage cannot instantaneously change. So what is the value of V of t at 0? V0 minus, which is going to be equal to V0 plus? 0. So it's going to start at 0, right? And then, what is the V infinity? Vs, right? Because at infinity, there is not going to be any current flowing through this resistor, which means that the voltage across this thing is going to be 0, which means that this voltage is going to be equal to that voltage. Right? And that means that this is going to reach an asymptote of infinity, of Vs at infinity. And how is it going to do that? Is it going to be like this, or is it going to be like this? Like that, right? Because it's a negative exponential. And what is the time constant of this exponential? This is important because you are not defining the exponential otherwise. R times c. So if I write this using that expression that we derived, write an expression for it, V of t is going to be Vs times 1 minus e to the negative t over tau, or t over rc, u of t. Agreed? Why is that? Look at this. If t is equal to 0, this is 1, so 1 minus 1 is 0, so this gives you 0. If t is infinity, this becomes 0, so you have Vs times 1. So you go from 0 to Vs. Make sense? Everyone's comfortable with this? Yes? So this is Vs, right? Lowercase Vs, Vs of t, or V in of t. You can actually make it even, if you want. Let's change this to V in, because I called that Vs. So it's jumping up simultaneously. This voltage is jumping. But for the voltage of the capacitor to jump, you remember the voltage of the capacitor is the integral of its current. For an integral to jump, its argument needs to be infinity. right? For it to have an instantaneous jump, for it to become discontinuous, essentially. And can you have infinite current when you have this resistor here? No, unless this resistor is 0. Which in fact you can see, think about it, if R was 0, what would happen here? The time constant is 0. It means that the exponential would get to infinity instantaneously, so which basically means that it would jump up. Instantaneously gets to Vs. Because as you reduce R, it becomes more and more rapid. So this is R increasing, or tau increasing, if the C was constant. Right? Make sense? So it has to be a smooth transition, right? Versus parameters. So it has to work in the limits too. So this is the step response of the circuit, really. You can actually think about it as S of t, right? The step response of the circuit. What is its impulse response? What is the impulse response of the circuit? So in other words, if V of S were to be so if V in, so now, what if V in of t is some Vs delta of t? Now, we'll see the unit-wise, this is a little bit tricky. We'll talk about that in a second. But we'll leave with it. We'll stay with it for now. We'll live with it, but we'll see what happens. I'll talk about the units later on. So although it may look like, oh, the units seem fine. The problem is that the units of delta, you need to think about what the units of Dirac delta are. And Dirac delta is not a unitless quantity. We'll see in a second. We'll talk about that. Don't let that distract you. Trust me, I'll get to that. So for now, don't worry about the units of delta. Okay? Just ignore it. Let's say we have some constant here that will adjust that unit. Turn it into a voltage. Right? Just forget about that. But other than that, if I hit it with an impulse now, so my V in of t is an impulse. How do I calculate the impulse response in this circuit? How do I find what the V of t is? The impulse can change this voltage instantaneously, right? Because it's a current of infinite value. So it will change that voltage instantaneously. It will jump. How much is the question? So to find out how much does it jump, you have to know what the current is, right? Through this capacitor. What is the current through this capacitor? So what is I of t going to be if you know the voltage? Now, this voltage as time t equals 0 is jumping to an extremely large value. What can you say about the current? Can someone think of what the current would be? In terms of that voltage. Let's say you know this. Can you write an expression for I of t in terms of this? In terms of that voltage? Right? Think about it. If this voltage is infinity, and this voltage is finite, what determines this current? Which one of these two voltages? The infinity one, right? Because it's an infinity minus the finite divided by r. Right? So for that time t equals 0, it doesn't really matter what this voltage is as long as it's finite. Right? Because you remember, what's the current through this resistor? It's this voltage minus that voltage divided by the resistor, right? So it is Vs delta of t. So this is exactly at time equals t equals 0, right? And minus some finite quantity. It doesn't matter, right? Divided by r. So that's the current around t equals 0. Do you agree? At t equals 0, it's that voltage, that huge voltage divided by the resistor. So that's what the current is going to be. So what is the voltage across the capacitor in terms of its current? So the V is 1 over C, right? Integral from negative infinity to t of the current dt. But I'm really interested in the vicinity of 0. So I'm basically integrating this from 0 minus to 0 plus. And what is the current? This guy, over in that vicinity, in that neighborhood of 0, right? Do you agree that it is this current? If you're not convinced, you have to stop me right now, right? But do you agree, if you agreed with that statement, that this is going to be the V of t? In other words, basically this is delta V. This is really delta V from 0 minus to 0 plus. That's the change in the voltage. That's the instantaneous jump. Because I'm integrating it from 0 minus to 0 plus. That's what's going to happen. So what is that integral? So Vs and R are factored out. It's the integral from 0 minus to 0 plus of delta t prime dt prime. What is this integral? 1, right? Definition of delta. So this is Vs over Rc, or Vs over tau. So this jumps, so it says that the voltage V of t versus t, it starts from 0. At t equals 0, though, jumps up instantaneously to Vs over Rc, or Vs over tau. And that's my V0 plus. So this is my V0 plus. And you can start to see probably the problem with the unit. We'll get to that. But just bear with the unit for now. And I'll tell you what the problem is. Now, what happens from that point on? You know the V0 plus. Now you can use that expression, right? What is V infinity? At infinity, you have a voltage source whose value, now at all times after t equals 0, this voltage source is 0, which means that it is what? A short circuit. So you have a resistor and a capacitor in parallel. So at infinity, what's the voltage across the capacitor? 0, right? The capacitor is going to be completely discharged at infinity. So it goes back to 0. And how would it do it? Would it do it like this, or would it do it like this? It has to always asymptotically reach its infinite value. Remember that. Therefore, this cannot work, because this will just stop here. And what is the time constant? Tau, which is Rc. So it goes to 0. So this is the impulse response of this circuit with t. So if I write an expression for it, it would be V of t, which would be V infinity, which is 0, plus V0 minus V infinity, so which becomes Vs over Rc, or Vs over tau, e to the negative t over tau u of t. Right? Everything is good and nice except for that unit, the mess with the unit. What is the mess with the unit? Let me ask you a question. What is, so this is a side note. What are the units of delta of t? So let's say, think about the definition. A delta of t, let's say, from negative infinity to positive infinity is equal to 1. What should the units of delta be if it's 1 unitless? 1 over second, right? 1 over time. So because it's multiplied by time and produces a 1. If I say delta of x position, dx from, I don't know, negative infinity to positive infinity of some position, the spatial delta. What is the units of delta? 1 over meters, right? So this is going to be 1 over meters, and this is going to be 1 over seconds. Now, and in general, essentially the units of delta are inverse of its argument, the units of its argument. 1 over the units of its argument. So remember that. The problem arose from the way I defined the input. Because this thing doesn't have units of time to begin with. This has units of time over second. And you can see its output also has units of, volts over seconds, not time, volts over seconds. Right? And this has units of volts over seconds. So if I wanted to make this correct, really I had to multiply it by 1 second. So this would have been Vs times 1 second for this to have units of voltage. And therefore that would have propagated through the whole thing, and this would have been like a 1 second up front. We have dropped that because I didn't want to make this complicated about something else. That was not the point of it. But just keep that in mind. So that 1 second would have propagated and compensated this tau, this RC in the denominator. So there's nothing wrong with that, fundamentally. Now, could I calculate this impulse response in a different way? I knew the step response of the circuit. And I know this is an LTI system. What is the relationship between the step and an impulse? We talked about this, right? What is the relationship between an impulse and a step? How do you get an impulse from a step? Differentiate, right? It's a derivative. So delta of t is d dt of u of t, which we wrote as p u of t. Right? You remember that? Because the integral of that was the integral of u of t. You remember integral of delta of t from negative infinity to t was u of t, right? So if delta is the derivative of the step, so if you think about this, this is the system, right? The system. So we put a step in, u of t, it gave us s of t, this response, the step response. Now, if I put in a delta of t, and I get h of t, if this involves a differentiation, or d dt, if I need to differentiate the input to get from here to there, as long as the system is linear, what do I need to do to get from here to there? Differentiate. Because if the system is linear, then I can switch the order of differentiation with the operation of the system. Then, so this should be the derivative of that, according to this. The impulse response should be the derivative of that. Is that true? Right? If you differentiate it, the first term, well, it's a little bit tricky, though. It's a little bit tricky. Differentiating this, you have to be careful. It looks like it is exactly, but let's look at it, see for sure. Because there's one thing, one subtle thing there. So here's the subtle thing about it. I'm going to reproduce it here. V of t is Vs 1 minus e to the negative t over tau u of t. So what is d v dt? Or this is, let's call this s of t, it doesn't matter. Then it would be h of t. ds of t dt. So what is the derivative of this with respect to time? So what are the things that are functions of time? There are two things that are functions of time. Be careful. One is e to the negative t minus tau. The other one is u of t. So it's the derivative of the first one times the second one times plus the derivative of the second one times the first one. So what's the derivative of the first one times second one? So it's Vs. So this term gives you 0. You get a negative from here. You get a minus, another minus from this 1 over tau. So you get Vs over tau e to the negative t over tau u of t. Right? So that's the derivative of this times that. All good and nice. How about the second term? is the derivative of this times that. What is the derivative of the delta, u of t? Delta of t, right? So it becomes Vs 1 minus e to the negative t over tau delta of t. So this term is a reasonable term. Let's look at this term. So what is this term at all times other than t equals 0? 0. Why? Because it has delta, right? The delta is 0 at all times other than t equals 0. So I don't have to worry about it at any other time. So the only thing I need to evaluate really is delta around 0, delta of t, and then this evaluated at 0. What is this evaluated at 0? 1? No. 0, right? This is 1. So 1 minus 1 is 0, right? So this is 0. But this is identically 0 at t equals 0. And that's why you don't care about this. So what you're left with is this, if you really want to think about it. You can, there's a way of doing this a little bit more rigorously. And you can go back to the definition of delta, write it, for example, in terms of p sub delta, in terms of pulse, and do that calculation and do the limit, and you will see that the limit goes to 0. Because technically, you're doing a 0 times infinity here. So you have to really resolve it more carefully. But you can do that. And you will get this result. So the impulse response is this, which is consistent with what we calculated directly. Does it make sense? All right. Okay. So okay, so that's it for now. Let's just stop.